I'm happy to present SCONE today. SCONE was actually worked on by my PhD student and my postdocs, so I'm just happy to be here and present their work. But you can get their papers on SCONE Docs, so if you want to get more details, just go to that website. Will be also on the next slides. Let me start with the motivation. I have only 15 minutes, so I cannot go into many technical details, so I give you some very high-level motivation, what we have been doing and why we have been doing that. And so our motivation is to help application developers to protect their application against attackers. So there might be some attackers that have motivation to steal my data, and if I'm an application provider, so typically I take the role of that, I want to protect my data, my computation, actually also my code, and all the communication. And so we want to protect integrity and confidentiality of my application data and computation. And we would like to do that in a context where we cannot trust the system administrators, nor the administrator of my service platform. And the reason for that is that these days we often want to take our application, not only run it in our trusted data center, but we also want to move that to an external provider. And we actually not only want to kind of rent resources, physical resources, but also kind of use other service provider to run our application. So one of the keywords is function as a service. So we would like to outsource that, and still, as an application provider, I want to keep control over my data. And so therefore, we don't trust the system administrator, and we don't trust the service provider, administrator, whatever that is. And so, and why don't we want to trust them? Because if they have credentials such that they can be stolen by attackers, they are targeted typically by these guys. So they go and get their credentials, even if the system administrators might be trustworthy. So, and when I am an attacker, now I take the role of the attacker, if I have root access to a system, I can use, for example, Linux functionality to dump the main memory of my application, or some other application, not mine, and get all the secrets out there. Because typically you have secrets or encryption keys that are stored in main memory, for example, decrypt files, and I can get all these secrets, and there are even tools that help me to identify what are secrets. So what we cannot trust on is that the operating system protects our secrets, and instead what we want to do in SCONE is that we allow end-to-end encryption, so that all the communication is encrypted, all the main memory is encrypted, and also all the files in the file system are encrypted in such a way that only I, as an application owner, are in control of the keys for encryption and decryption. So that means that somebody who has root can manage my resources, but this person cannot steal my secrets. So that these are our goals. And of course, you will say, oh, encryption of main memory will be really slow, and you're right if I do that in software, but if I have some hardware support like Intel SGX or some other CPUs, I actually can achieve a reasonable performance. Of course, it's not for free, but there is a reasonable performance, overhead only. And so what we are focusing on in the SCONE platform is to help application providers to actually move their application in such trusted execution environments like Intel SGX or other alternatives. And so we had a first paper in OSDI 2016, and there we showed that you can take a container-based application and move them into trusted execution environment with hardly any source code changes. And there, our motivation is really, we want to avoid source code changes as much as possible, because the application designer, they are typically not interested in spending resources on that, nor might they have the staff to actually do that transformation. So we want to make it as transparent and as simple as possible, so you get additional security without lots of engineering effort. And so right now we support multiple languages, C, C++, Go, Rust. Some of them I would not recommend to use if you have the choice. So better use some safe languages if you run inside of such enclaves. So we try to use Rust these days whenever we can for our own software. And so our original motivation was to support so-called cloud-native applications. So cloud-native applications are typically deployed with containers. There are multiple microservices, each runs in their individual container. They talk to each other to provide a common functionality. And sometimes or the vision is at least that they also run across multiple clouds. So you have some edge service, some regional cloud where you run some services, and also some back-end services. And these days we want to move on, not only cloud native, we want to kind of generally support application also in the IoT domain. But the problems that you face are very similar, sometimes even harder if you're in the IoT domain. And one of the problems that I want to address here in this talk is how can we actually make sure if I say this microservice, that I really talk to a microservice that belongs to the same application, not from somebody else's, or is not under control of some other, say, attacker. So we need somehow to make sure that when we talk to another entity, and if that should belong to the same application, that it indeed belongs to the same application. So we have to do some attestation or authentication. So, and that is, to understand what attestation is, and I will briefly talk about it, is really difficult. So we want to also make it as easy as possible for the application designer or developer to attest each other or the microservices of that application without having to re-engineer a lot. So therefore, our assumption is that these days, at least in the cloud-native domain, we have microservices or services, they talk to each other via REST APIs typically, and we can protect these REST APIs using TLS. So we have HTTPS as transport. And so if we are in such a domain, and this is a very popular domain these days, so this application domain, then we can actually use TLS functionality to do authentication, and that in turn is actually attestation of the functionality that we talk to. And in authentication, I can make sure if I'm a client, I talk to a server, I can verify that this server has the right certificate, and vice versa, the server or the service can verify that I, as a client, have also the client certificate. And we kind of use that mechanism to hook into what we call the attestation mechanism. So we want to make sure, again, when we talk to each other, that we run the right code, and we actually want to verify more things. So we want to make sure, if I talk to you, that you run the right code that I expect, that your file system is in the right state, so we actually transparently can encrypt files. We have a Merkle tree across these files and kind of can identify the current state of the file system with some, what we call a tag. And so that means when I do attestation, I can verify that not only the right code is running, that the file system is in the right state. And in the near future, we hope that we can also ensure that you are running in the right operating system environment. So we want to hook that in with also some trusted, secure boot functionality. So in this case, what we do is we have a service in the SCONE platform, which we call the configuration attestation service. And that CAS, for short, allows an application that starts up to get a certificate. So in practical sense, you run your application, you actually don't know that there's attestation going on because our runtime gets control before your application, and then the runtime connects to this CAS service. It shows, okay, I run this code with the help of the CPU. The CPU gives it kind of a so-called quote saying, okay, this code was started, and I take that quote and then send it to the CAS, and the CAS, if it's happy, expects me to run this code, it will get a certificate back to me. And I can then use that certificate to talk to other microservices. Okay, that said, I can use then the certificates to talk to other guys, or to other entities. And what I have to deal with in practical settings is that we have typically horizontal scalability. There might be many services in my application that I have to talk to. I have to somehow make sure that we are really in the same group. And so what we also will support very soon is kind of a certification authority as part of our attestation service. So you can, as an application designer, you start your own certification authority, and then you can use that certification authority, the certificate of that, as a root certificate for TLS, and then you automatically will make sure that you only talk to the right entities. So there we really want to make sure that it's as easy as possible to make sure that you only talk to your own microservices. Of course, when you talk to external services, there you have to do some extra firewall rules. So there we don't help you with. What I actually want to talk to you about today is a little bit about the secrets management. I already get the 5-minute sign, so I'm try to be quick. So when you run these applications, you have to have some secrets, some keys, and how can I manage that? So of course you could use a secrets management service where you can create keys, where you can get keys, but there are some nice ones around, but there you might have to change your application. So what we want to support you with is, if you are in a containerized world, you typically expect that your secrets come via command line arguments, environment variables. At least if you go to Docker Hub, there you can find lots of services, and they expect that you configure them via these environment variables. So what we actually also provide you in SCONE is that you can create secrets, or you can store secrets in this configuration service. We do the attestation, and after your service passed the attestation, we can provide this service with command line arguments that might contain secrets that you stored in our service, or environment variables, and we do it via TLS channels. So we don't pass these arguments to Docker or your Kubernetes cluster, and so we just have a direct TLS connection such that the application gets these secrets via a secret channel, and also for the application it doesn't really realize that the arguments or the environment variables was sent in some different way to it. And what we also have, what we are currently working on, I should say, is also to provide injection of secrets in files, and I want to motivate that a little bit, why you might need that. And therefore I present my favorite example, MariaDB. It's a nice database. It provides you with some encryption facility. So if you have tables, you can give it keys, and it automatically can encrypt these tables. The problem is, how can you actually, where do you store the key for the encrypting your database tables? And so there are multiple ways, and one of the common ways is to store that key in a configuration file. And that configuration file is actually not encrypted, because you would need a key to decrypt that configuration file. So there you have a little problem. And so what we can provide with SCONE, because we have that attestation, we can actually transparently encrypt that configuration file. So to MariaDB, it just reads a file which seems to be unencrypted from Maria's point of view, but from the application point of view, or from the enclave perspective, it is completely encrypted in the file system, and only the MariaDB can decrypt it. And then the next step might be, you still have to store that key in there, in this configuration file. And that might be visible to some administrator that might leave your company next week, and then you have the problem that you have to change all the keys, you have to regenerate the tables, and you have all kinds of problems. And so therefore we have in the pipeline a new research work, where we actually allow you in certain files that you specify, put in variables. And so these variables they are not secret. They are just kind of variables for secrets. And then when your application reads these files, you inject the actual secret that was automatically generated in your cache, which is not on the slide right now. And so in this way, what we want to provide you with, as an application designer or service provider, a mechanism to keep the secrets completely secret from all your employees or people you don't completely trust, and keep that all inside of trusted execution environments. Only if you would like to do that. So there is some mechanism to do that. And then, of course, people ask, okay, but then the way to attack that system is actually to change the security policy, because there has to be some policy that specifies who can read the secrets or who could modify it or create that. And so therefore, in this next version of our system, the CAS, we addressed that issue, and we actually copied some ideas from blockchain community. So there you can have policy boards that decide about security policies. And so that's what you can also specify. If you have an application, you specify your security policy. And there you say, I have a security board. And that, or the policy board, I say it here. And that policy board, you can say it consists of a set of humans, and you can also have a set of scripts. So the scripts can be used to verify that certain, say, enterprise constraints are satisfied, and they reject policies that are not satisfying these constraints. And we have then also, say, some humans, and some of them might be malicious. They might have some other incentives why they want to change the security policy. But you're in control when you specify the security policy, how many of these policy board members actually have to approve a policy change. Now I have 1 minute left to talk about implementation. So our original implementation was Intel SGX. We started 2015 before the hardware was available to build that. We have no library OS inside of our trusted execution environment. We just have a libc there to make sure we have small code base. Also, it allows us to better support certain forms of forks, vforks. We have an approach, so I'm now going really fast. We have an approach where we try to support different technologies. So we have Intel SGX. Right now, we want to make sure that we can support different CPUs. We also want to have the main memory encryption of Intel, for example, or AMD. So in that, we can achieve by having cross-compiler support. So we take the source code, and we cross-compile it for the right trusted execution environment. I have one performance measurement. So everybody is interested in secure analytics on machine learning. So therefore, here I have some example of PySpark. So it's the Python version of Spark. We can run the JVM in enclaves. We can run Python workers in enclaves. And then the question is, how much overhead do we have? Because Intel SGX is really, well, limited in the hardware that it has, or the caching. But in this context, just to give you a preview, about 22% overhead in this context. Reason for that is there are other overheads that they are not affected by running that in trusted execution environment. So therefore, the total overhead is actually acceptable. There are different applications will have different overheads depending on which domain you are, how much memory you have to access. There might be more or less overhead that you see. And that was my talk. Thank you for attending that. If you have questions, thank you.
Nick.UCI. On slide 17, you said that you'd use cross-compilers to go to different platforms. So that seems to be a big security risk, right? Because you're using some compiler, and how do you trust what
your compiler does?
Yeah.
That is true. So we have to trust the compiler, but I think, so there are, of course, compiler approaches that try to make sure that what you compile is what you really want. So we have actually some projects in the pipeline, some research project, where we exactly look at that issue, because that is, there are some attacks on software development processes where attackers actually introduced code in this stage. And so we are actually working on that one.
Further questions?
Hi, Aviral from Arizona State. So you mentioned that for some scheme you want to control the clients. You want to do some tests on the client and see if everything is okay.
Yes.
There, right? Are they executing the code that you have verified? So, yes. Because you are controlling the clients or even checking, right? Isn't that a security risk? Like if the server is compromised, then?
Okay. So I think your question is, how do I figure out if a client executes the correct code?
No, my question is, how can the client be sure of the server's intention?
Okay, so how can I, so if I'm a client and I'm using some external service, I think we have to distinguish between different cases. First, what I presented here is kind of the clients and the service belong to the same application. So they are internal clients. So that's how you build these days cloud native applications. And there I can make sure that if I build the application, I know kind of the hash of the code that runs in the service and in the client, and that is kind of translated into some TLS certificates. So there I know what I want to have. Now, the bigger question is, if you provide an external service and I'm an external client, or we don't belong to the same application, then we have some different problem. And this is a very interesting problem, how to solve this, but I think you can use the same technology. If I know your source code, and say you have open source, I can actually verify that you run exactly that source code. We have to be really careful that the source code doesn't allow any configuration that allows you, allows you to get to my secrets that I have. But I think there is a principal solution to that if you limit the configurability of certain application or services. Okay? Yes, please.
Sorry, we have to come to an end at this point. Take this offline. Okay, let's thank the speaker again.